Hi everyone, what's up? Welcome back to my tutorial channel. Today we are going to do some IFM practice of topic 10a, option price partial derivatives. So in this video I'm going to do 10 problems. Each of these I collected from the IFM exam. Let's look at the first problem. Problem number 1. Assume Plaxico's framework. For a non-dividend paying stock, you are given the stock volatility is 25%, the continuously compounded risk-free interest rate is 12%. If a year 12 tri-European call on the stock has a delta of 0.3859, find the price of the call option. Before we solve this problem, I would like to take a moment to summarize the question using notation because it helps a lot when I solve the problems. Alright, so here, just read the sentence one by one. Assume the Plaxico framework. This is the assumption. You see, this is the assumption. Now, for a non-dividend paying stock, you are given non-dividend paying stock. That means delta is equal to 0. So I'm assuming right delta here is 0. See that delta is 0. The stock volatility 25%. So I have sigma is 0.25 or 25%. You see, I'm assuming right the question on top of this page. Now the continuously compounded risk-free interest rate is 12%, which means R is equal to 12%. See that? And then a 1 year 12 dry European call on the stock has a delta of 0.3859. Here, the third information gives you 3 numbers. 1 year, 12 dry, and 0.3859. So we got T, the duration of this call is 1 year. The strike is 12. And we got the delta of it is, this is delta call. Delta call is 0.3859. See that? And the question asks for the price of the call option. So now we have finished summarizing the question. In order to find the price of the call option, we need to write out the formula. Remember that the call price here is equal to the current stock price, which is S0, E to the minus delta T, 5 of D1. Some people use N of D1. Doesn't matter. As long as you know this is the CDF of the standard normal distribution. Minus Kate, E to the minus RT, phi D2. See that? Phi D2. So, now let's take a look at this one. I'm going to use different color. Alright, so, in order to find the price of the call option, we need to know S0, but S0 is not given, right? This is not given. E to the minus delta T, delta is 0, T is 1. So this is E to the 0, which is 1. So this is given. Now phi of D1, we don't know D1, and we don't even know the CDF of D1. So this is not given. K is given at 12, right? K is given. E to the minus RT, R is 0.12, T is 1, so this is given. See that? Phi of D2 is not given. See that? So, basically we need to find S0, D1, D2, phi of D1, and phi of D2. So we need to find these information, right? So let me use different color here. So here we need to find D1, we need to find D2, we need to find S0, we need to find phi of D1, we need to find phi of D2. See that? So we need to find these information, right? We need to find the information. All right. So now, let's see which one is easier to find. We haven't used anything about delta car yet, right? Here we have delta car is 0.3859. But our question is how to use it. Just write out the formula of delta car. Remember, delta car here is the partial derivative of the car price respect to the stock price. So we got delta here is just delta C over delta S0, which is e to the minus delta T phi D1, right? But e to the minus delta T is 1 because delta is equal to 0. So this is just phi of D1. You see that? Phi of D1s. So leading to what? Leading to delta here is 0.3859 and is equal to phi of D1 is what? This is phi of D1, right? So just use normal table distribution. D1 should be the invert norm of this number, right? You either can use technology or you can use the table. But of course for IFM you don't have technology or high quality calculator. The only calculator you can use is the TI X30XS. So you really need to know how to use the standard normal distribution. It's very easy to use. And if you use the table, then we got D1 here. D1 is equal to phi inverse of 0.3859, which is negative 0.29. So yeah, negative, give me a second, negative 0.29, negative 0.29. So yeah, so now I have figure out D1. Right, I'm gonna write, let me just erase this one and this one. So now I got a new information. I got D1 is negative 0.29, right? And don't forget that phi of D1 is 0.3859, right? We need to find D2, phi of D2 and S0, right? Now D1 is given, phi of D1 is given, right? Alright, so from D1 here, now we are going to find D2. And don't forget that D2 is D1 minus sigma square root of T, right? D1 minus sigma square root of T. So it should be negative 0.29, subtract 0.25, square root of 1. And it should be negative 0.54. See that? So by the way, let's find phi of D2. Phi of D2 here basically is just probability that Z is less than or equal to minus 0.54. You see that? So it should be, just use the table, the Z table. This should be 0.2946. See that? This is by Z table. Okay, by Z table. Okay. So now I have new information. Let me write down the information. I don't want to forget it. So D2 here is negative 0.54 and phi of D2 is 0.2946. Now how to find the stock price, the current stock price? So let me change the color again. The stock price, remember that S0 is in the formula of D1 and D2, right? So in order to find the current stock price, You can either use D1 or D2, whichever. Here I'm going to use D1. I'm going to write down the formula of D1. D1 is equal to natural log of S0 over K plus R minus R plus delta, right, plus delta minus sigma squared over 2 square root of T over sigma square root of T, right, and delta here is equal to 0, right. D1 is given, T is given, sigma is given, R is given, sigma is given, K is given, so it's very easy to find S0 from here, right. Now let me erase the board so that I can have more place for this problem. I'm going to erase my work here because we already got D1, D2, right? I'm going to erase this part. Alright, so now using this table, this formula, we are going to find S0. So D1 here is what? Negative 0.29 is equal to natural log of S0 over 12 plus 0.12. Delta here, the dividend rate is equal to 0. And sigma here, the volatility is 0.25 square over 2. Okay, square root of 1 over 0.25. And just solve this equation for S naught. This is an equation of one single variable, right? It's a very easy equation. So just use your calculator. You're gonna have S0 is equal to S0 is equal to 12 e to the, give me 1 second. It should be equal to 12 e to the minus 0.29 times 0.25 plus 0.25 square half minus 0.12. See that? And S0 here is equal to S0 here is equal to 9.59. Just use your calculator to verify it, okay? So now we got another information. That is S0 is equal to 9.59. See that? So now we got all we need, right? We got all we need, right? This one I'm gonna use a brackets so that you understand all of these are on the exponent. This is a very easy equation, okay? It's very easy to solve for S0. Alright, so now I'm going to erase everything again because I'm just going to use the information. Okay, so I erase my work here. I don't have many pages here, sorry. So I erase everything here. Alright, so how to find the call price here? I'm going to use an equal sign. S0 is 9.59. E to the minus delta t is e to the 0. E to the 0. Phi of D1 is 0.3859. See that? Minus 12. E to minus 12. Negative 0.12. Phi of D2 here is 0.2946. See that? So eventually, just use your calculator. The answer should be 0.57. Excuse me, 57, not 59. 0.57. And this is the answer. Okay, so the answer is 0.59. This is the call price, the price of the call option. So that's the first problem. See that? Alright, so now let's move on to the next problem. Problem number 2. Assume the Plexical framework, and which of the following is our true or false? You see that? So we have to read these statements and decide whether they are true or false. Okay. The first one, and don't forget this, these statements are based on European car and put option on a stock with no dividends. Okay, no dividend. So the first statement, row of the call option is positive. Then we got row of the put option is positive. With the same underlying access, a stock, strike price, and time to expiration, the row of European car is the same as the row of the European put. So this is the statement. So now we are going to verify whether they are right or wrong. So the first statement, for this one, in order to know whether it's right or wrong, we need to write down the formula of row. Remember, row is notated by this notation, right? And row is the partial derivative of V respect to R, right? Respect to R. So for European car and put option, remember for car, the price of it is S0 e to the minus delta t phi d1 minus k e to the minus rt phi d2. So if you differentiate with respect to r, we got row here is very row here should be S0. Remember, R is included in D1, right? Don't forget that D1 is equal to natural log of S0 over K plus R plus delta minus sigma square over 2 square of T over sigma square of T. And this is R. You see it, we got R in that. So for this one, we got S0 e to the minus delta t, little phi of D1, time with, this is capital phi and this is little phi. Okay, little phi is the PDF. And we got partial derivative of D1 over partial derivative of, this is over delta R, the partial derivative, plus K e to the minus RT phi d2, right? And don't forget this is Brock rule, so we have to plus minus K e to the minus RT little phi of d2 partial derivative of d2 over delta R, right? Delta R. So for this one, row D1 partial derivative D1 over dr. You see that the partial derivative of D1 over dr is always positive, right? This is positive. This is also positive. And we notice that this part is positive. This one is positive. So basically we got row of the call option is always positive, right? You can take a look at each of these. You're going to see it. This is going to lead to a positive term. And do similar for put option. For put option, you're going to see it's flip side a lot, because basically it's k e to the minus rt phi minus d2. For the put option, this is the price of it. So first of all, one is correct, okay? And for the put option, minus S0 e to the minus delta t phi of minus d1. And when you differentiate respect to r, when you have it, this is minus k e to the minus rt phi d2 minus plus k e to the minus rt little phi d2. Remember, capital phi and little phi are different. Partial derivative d2 over, it should be partial derivative minus d2. This is phi minus d2. So this should be minus psi right here. You see it, minus psi over delta r. And minus this one, right? Minus S0 e to the minus delta t little phi of d minus d1 partial derivative minus d1. So this is plus d1 over delta r. And from here we see that these coefficients are gonna have a negative terms, right? Negative terms. So in general, growth of put is negative in general. You see that? So it's not positive. So this is incorrect. Now for number 3, with the same underlying assets, strike price, and time to expiration, the row of the European car is the same with row of the European put. This is incorrect because the row of the car option is positive and the row of the put option is negative. So they cannot be equal. So this is false. You see it? Number 3 is false. So in short, we got 1 is the only correct statement. So answer 1 is correct. Right, 1 is correct. And that is the only correct statement here. See that? Alright, so let's move on. Let's move on. Number 3. Assume the Black-Scholes framework for option pricing. Which of the following are true about delta? Let me zoom it in a little bit. Number 1, the delta of European car option is positive. Number 2, the delta of European put option is negative. Number 3, the delta of a European car can be greater than 1. So we are going to justify these information, right? So first we need to write down the formula for European car option put option price, and then calculate and then derive the delta. Right, so first let's look at European car. European car. The price of the European car is C is equal to S0 e to the minus delta t phi d1 minus k e to the minus rt phi d2. Okay, so in order to find delta car is delta c over delta S0, right? And it should be e to the minus delta T over S, excuse me, this is just over delta S, over delta S, and it should be e to the minus delta T phi d1. You see that? And for this, we see that the delta of call option is always positive, right? But is it greater than 1? The answer is no, because e to the minus delta T is less than 1. Phi of d1 is also less than 1. So we got delta call is less than 1. You see that? So from this one, we got delta call less than 1 but greater than 0. That means 1 is correct, right? But 3 is incorrect, right? Incorrect. So that means 1 is true and 3 is false. See that? Now let's look at European put. European put. For European put, we got the put price is equal to K e to the minus RT phi of minus D2 minus S0 e to the minus delta T phi of minus D1. So from here, if we find delta put, we should differentiate respect to the stock price, delta P over delta S, and we got it should be minus S0. Oh, excuse me, no S0 in here. Minus E to the minus delta T phi of minus D1. You see it? Phi of minus D1. And phi of minus D1 here representing the probability. So it's positive. E to the minus delta T positive. With the minus side, this is negative. You see that? So we got delta put is always negative. Right. That means 2 is correct. So we got 1 is correct, 2 is correct, but 3 is incorrect. You see that? You got here 2 is correct. See that? Very easy. So we see that 1 is correct, 2 is correct, but 3 is incorrect. Alright, let's move on. Now for problem number 4, assume the Plexco's framework and consider a stock and a European call option and a European put option on a stock. The current stock price, call price, and the put price are 45, 4.45, 1.90 respectively. And investor A purchased 2 calls and 1 put. Investor B purchases 2 calls and writes 3 puts. The current elasticity of investor A portfolio is 5, and the current delta of investor B portfolio is 3.4. Calculate the current put option elasticity. So here, let's summarize the question. The current stock price, call price, and put price are 45, 4.45, 1.90 respectively. So we got S, the current stock price at 0 is equal to 45. The call price, C, is equal to 4.45, and the put price is 1.90. This is put price. Okay, put price. All right, investor A purchase. This is purchase, right? Purchase. So if we look at A, he purchased 2 call and 1 put. See that? And investor B, he purchased 2 cars, but instead of purchasing 3 puts, he writes 3 puts, so it should be subtract 3 put. See that? Now the current elasticity of investor A. So we got omega A is the elasticity, right? And omega A here is equal to delta A time with S over P, right? Over P. Over price. Over price. So it should be delta A here is what? Delta A here is 2 delta car. This is car, okay. And this is put. This is car. And this is put. So it should be delta car plus delta put time what S is 45 over the price of it should be 2 times 4.45. Hold on, give me a second. Let me erase this. So omega A is 5, right? Delta A here is just 2 delta car plus delta put, right? Delta put. S is 45, which is given the current stock price, over the price of the portfolio of the investor A. Investor A purchased 2 cars, so it should be 2 times the price of the car plus 1 price of the put. So it should be 2 so we got 5 is equal to 2 delta car plus delta put time with 45 over, let me use a calculator, 2 times 4.45 plus 1.9, it should be 10.8. See that? And from here we have an equation, 2 delta C plus delta P is equal to 5 times 10.8 over 45, which is 1.2. It should be 1.2. So this is one equation, right? And investor B, delta B is 3.4. We got delta here, delta B is equal to 2 delta car minus 3 delta put. And delta B is 3.4 is equal to 2 delta C minus 3 delta P. See that? So we got, remember this is another equation, right? So now we have a system of 2 linear equations. Okay, this is one, and then the second one. Solve this linear system. We got here 3.4 is equal to 2 del C minus 3 del P. 1.2 is equal to 2 del C plus delta P. So now if you subtract side by side, you got this is 2.2 is equal to minus 4 delta P. Right, delta P. Leading to delta P is minus 2.2 over 4, which is minus 0.55. See, minus 0.55. So now we go to another stage of it. We are going to calculate, and we use different color. The current put option elasticity, that means omega put. omega put is equal to delta put times with the current stock price over the price of the put option, which is P, right, over P. So it should be negative 0.55 times with 45 over the price of it is 1.9. It should be minus 13. It is equal to minus 13.03. See that? See that? That is the elasticity of the put option. See that? So the answer is minus 13.03. See that? Negative 13.03. Let me fix my minus sign. See it? Minus 13.03. Alright, so that is problem number 4. Now let's look at problem number 5. The Plexco's framework. The Plexco framework. Which of these statements is or true? Number 1, psi of the change in the option price from a 1% increase in the continuous dividend yield on the stock. Number 2, psi is positive for European call option on a stock that pays continuous dividends. Number 3, with the same underlying assets, strike price time to expiration, the psi of European call is the same with the psi of European put. That's question number 5. So in order to answer this question, we need to write down the formula of psi. Remember, the psi is notated by this notation, and it's equal to delta V over delta. That means like partial derivative of the price, the value of the price, respect to the dividend yield rate, right? So psi is the change of the option price from 1% increase. Of course, this is by definition, so number 1 is correct because it's the definition of psi. Now number 2, psi is positive for European call option on a stock that pays continuous dividend. So if we look at European call, the call price is equal to e to the we don't forget S0 e to the minus delta t phi d1 minus k e to the minus RT phi d2. So now if you differentiate with respect to delta, then remember within D1 and D2 we also have delta, right? We also have delta. So if we differentiate it, we got psi is equal to S0, it should be minus S0 t e to minus delta t phi of D1 is little phi of D1 partial derivative D1 respect to delta minus oh no, this is my bad. Should be phi D1. We have to use block rule for the first terms. Plus S0 e to the minus delta t little phi of D1 and partial D1 respect to delta minus k e to the minus RT little phi of D2 partial derivative of D2 respect to delta. Alright, so if we look at the formula of D1 and D2, D1 and D2, you see that the first term here, let me change color. The first term here is negative, right? This is negative. Now for the second terms, so this is negative plus, I'm going to use the side. The second terms, we need to pay attention to first derivative of D1 respect to delta. Remember that D1 is natural log of S over K plus R plus delta minus sigma squared over 2 square root of T over sigma squared of T. So the first derivative of D1 respect to delta is positive, right? It should be positive. It should be positive. And the second terms, it should be also positive. So that means this one we cannot say whether psi is positive or negative, right? This one, we got partial derivative of D1 respect to delta is positive. So we cannot say anything about this. So this is incorrect. And with the same underlying access and dry price and time to expiration, the psi to European call is the same as the psi of European put. This is incorrect because for call and put option, the price of it are written in different formulas, right? So it's incorrect. So the only statement that is correct is 1. Alright. Next problem. Assume the Black-Scholes framework. Which of the following are true about theta? Theta of European call. Theta is always negative. Theta of a put option is equal to theta of call option. And remember theta is delta V over delta T. Right. Theta is always, the first statement, theta is always negative. Theta of a put option is equal to theta of call option if they have the same strike price and expiration date. Theta measure the change in the option price for a special unit increase in the time to expiration. It's not for a specified unit. It should be 1 unit. So this is incorrect. Now, theta of the put option is equal to theta of a call option if they have the same strike price and expiration. Let's look at the call price and the put price. Call price is S0 e to the minus RT, delta T. Give me 1 second. I think I make a mistake right here. For this one, we do not use the initial price. We use the time T price. At T, e to the minus delta T minus T, phi up D1 plus, not plus, it should be subtract K e to the minus r t minus t phi of d2. You see that? Phi of d2. So if we differentiate respect to t, delta c respect to delta t, this one, it should be in a long derivation, right? You see the psi of t is positive. So we got, is it positive or negative? D1 is natural log of ft over k minus r plus delta minus sigma square over 2 t minus t over sigma square root t minus t minus t. For this one, as I remember, it should be correct. This is correct. Theta of a put option is always negative. Alright. And number 2, theta of a put option is equal to theta of call option. This is incorrect because call and put option are written in different formula. Let's see, P is K e to the minus R T minus T phi of minus D2 minus S0 e to the minus delta T minus T phi of minus D1 . So this one is the only correct answer. 1 is correct. But 2 and 3 are incorrect. Alright, problem number 7. Assuming the Black-Scholes framework, which of the following are true of Vega for European put and calls? Vega of call is always positive. Vega of put is always positive. With the same underlying assess and try prior time to expiration, Vega of European call is the same Vega of European put. Vega is notated by this notation. It should be equal to the partial derivative of the price respect to sigma, the volatility. So Vega is always positive. Vega of the put is always positive. Remember, call option C is, again, C is S0. S0 e to the minus delta t phi d1 minus k e to the minus rt phi d2. So if we differentiate respect to sigma, remember that d1 and d2 has sigma in it. We got sigma in it. So if we differentiate it, this should be delta c over delta sigma, that is bigger, is equal to S0 e to the minus delta t little phi of d1. This is capital phi and this is little phi. Partial derivative of d1 respect to sigma minus k e to the minus rt phi of d2 partial derivative d2 respect to sigma. Alright, if we look at the formula of d1 minus plus r plus delta minus sigma squared over 2 sigma squared of t, the first derivative of it respects this is a long derivation. Figure of European put and cars. Put but it should be negative. This one should be negative because partial derivative of d1 respect to sigma is negative. So it should be, so this should be negative, and then the first derivative of d2 should be positive with a minus sign. So eventually vega here should be negative for call option. Vega here should be negative for call option. So number 1 is incorrect. Number 2, if you derive it, you got put option here. Put price is k e to the minus rt phi of minus d2 minus s0 e to the minus delta t phi of minus d1. If you differentiate respect to sigma, then you're gonna have is also negative. Basically, vega is always negative. So number 2 is incorrect as well. And number 3 is incorrect because for put and for price, we use different formula. So they cannot be equal. So 3 is incorrect. So the answer is none of them. Answer here is none of them. Yeah, that's problem number 7. None of them. All right, next. Number 8. European call option with 1 year to maturity. And a strike price K are available on 2 different stocks, stock A, stock B, over the next 10 days. Here we got the next 10 days. The price of one share of stock A increases by 2, while the price of one share of stock B decreases by 2. So that means epsilon of A is 2 and epsilon B is minus 2. See that? And we have a table. For call on stock A, we got delta A is 0.6. Gamma A is 0.1. And theta A is negative 12.410. Delta for theta B is minus 2. We got delta B is equal to 0.4. Gamma B is 0.5. And theta B is negative 10.950. And we got the call option price as today. We got call price, right? So now if we look at A, the call price of A, we got call price of T plus H, T plus 10 over 365. Because 10 days after, so H is 10 over 365 because we measure time by year. Minus CT. Basically, before we do this, I'm gonna do one more step. So from here, we have one more information that is H is 10 over 365. You see that? So if we look at the stock A, we got C of T plus H minus C of H. By delta, gamma, and theta approximation, it should be equal to delta A epsilon plus 1/2 gamma A epsilon, this is epsilon A, epsilon square, and plus theta A H. It's very simple. So now let's see. The stock price 10 days later is 4.2. The stock price of today, the call price of today is X, right? This is the call price, not the stock price. Is equal to delta A is 0.6 times what 2 is epsilon A, is the increase in the stock price. Oh my gosh. Times 2 plus 1/2. Gamma A is 0.1. And then this is 2 square plus theta is no need to plus minus 12.410 times H. Times H here is 10 over 365. See that? That is one equation. And from here we got 4.2 minus X is equal to, from here we got, this is, from here we can go ahead and solve for X. Just use calculator. Just use the calculator. We got X here is 3.14. 3.14. See that? 3.14. And if we look at B, the call price of B after 10 days, subtract the call price today is equal to delta B epsilon B plus 1/2 gamma B epsilon B square plus theta B H. It should be y minus phi is equal to delta B is 0.4 Gamma B is 0.05. It's the minus 2 square. Plus theta B is negative. So I'm going to use negative here. Negative 10.95 times H. H here is 10 over 365. So from here we got Y. If we solve for Y, we got Y is 4. And now we got X and we got Y. Right, I'm going to change color. So here we got Y minus X. Should be 4 minus 3.14, which is 0.86. See that? So this is the answer. Y minus X is equal to 0.86. See that? So this is problem number 8. Alright, next problem. Number 9. Number 9. For a stock you are given, the current stock price is 50. So ST is 50. The volatility sigma is 0.25. Risk-free delta is 0.02. Here we have in D1. I use 5, but in D1 is the same notation. A sigma 52 tries call. So T is 1/2. K is 52. Has a price, call price. Has a call price. So right now call price CT is equal to 2.72. ND1 here basically I use D5D1 is 0.4681 and gamma is 0.0446. Use delta gamma approximation, estimate the price of the call if the price of the stock increases to 550. So that means C of T plus H is equal to 50.5. And this is delta gamma approximation, so there's no theta in the approximation. So now we need to estimate the price of the call. If the stocks, oh my bad, this is not correct. This is not correct. The stock price increased to 50, so we got S of T plus H is equal to 50.5. Right, 50.5. Leading to what? Leading to epsilon is 0.5. So yeah, because epsilon here is the differences between the current stock price and the future stock price. Alright, from here, if we use delta gamma approximation, we got CT plus H minus CT is equal to delta. And delta here, remember for call option, CT, this is delta epsilon plus gamma. Epsilon square half, that's it, right? CT plus H is what we want to find, right? CT is given which is 2.72, right? Now delta, remember here we got theta, delta. Remember that delta is equal to e to the minus delta t, phi d1, or in this one we can use nd1. Oh my gosh, nd1, see nd1. So from this one, it should be e to the minus 0.02. T is 1/2, so we are going to divide by 2. My bad. So delta is 0.02, T is 1/2, so it should be 0.01 right here. And phi of N1 is 0.4681. See that? Which is equal to, give me a second. Which is 0.46. This is 0.46. Yeah, 0.46. Epsilon here is 0.5, right? Times 0.5. Gamma is 0.0446. Time with epsilon square is 0.5 square over 2. See that? And from here we can find the stock price. The car price. So it should be just from this equation, it should be 2.72 plus 0.06 of 0.46 times 0.5 is 0.23 plus 0.00446 times 0.5 squared over 2. It should be 0.005575. So it should be equal to 2.95. 2.955, so 2.96. See that? So the answer here, I'm gonna change color. So the answer here is 2.96. See that? That's the answer for this problem. That is 2.96. Alright, next problem. Number 10. This is the last problem. Let me make it bigger for you to read. The delta of 3 months call option on the stock is delta, and you are given that D1 is 0.12. Find the continuous yield rate. I'm going to use black color. Alright, delta of the 3 month call option. 3 months, so T should be 3 over 12 because a year had 12 months, and which is 1/4, right? Delta is given as 0.54. My bad. 5464. And D1 is given as 0.12. And now the question is, what is the dividend yield rate? The dividend yield rate. So, let's see what we can do with this. Remember that delta is e to the minus delta t. Either phi or n, you can use whichever. Here I use phi by statistics notation. It should be equal to e to the minus delta over 4. 5 of 0.5464. So just use the z table, okay? Use the z table. We got, this is what? If you use the z table. If you use a z table, this number should be, give me a second, I use my table. It should be 0.5478. 0.5478. This is 0.5478. See that? So now we can just plug into the equation. So we got 0.5464 is equal to e to the minus delta over 4 times with 0.5478. See, 5478. So from here we can solve for delta, right? We can solve for delta. So we can solve for delta from here. We got delta here. Oh my God. Delta here is equal to 0.01. 0.01. See that? So I'm gonna change color. So answer is 0.01. This is the answer. See that? So this is how we solve this problem. Alright. So that's it for today. Thanks so much for watching. I hope you guys enjoyed my video. Please like and subscribe my channel if it's helpful to you. I hope you studying well for the exam. If you have any question, if there is anything that you couldn't understand from the video, you can read me as daniela.tran2018@gmail.com. My name is Tran, or you can call me Daniela. Alright, so see you next time. Bye.